Blue tube. Get it straight.
Okay, let's look at the Navier-Stokes example that was done in class on Tuesday for week 11. So this is the last part of chapter 6 where we're talking about the full-blown Navier-Stokes equation. Well, at least the Navier-Stokes equation for Newtonian fluids, which is as far as we're going to take it. So remember, this one has the mass times the acceleration. There's the acceleration terms. And they're a function of the external forces, pressure, gravity, and shear is the new part that we added with the Navier-Stokes. So we have two plates. We have flow passing through these plates, only in one direction, so it's U, and V and W are equal to 0, so remember that. We have the coordinate system set up, so X is this way, Y is up and down, and the plate is 2h apart. Plates are 2h apart, so we have it going in the plus h direction here and the minus h direction here. So we want to show that the velocity distribution is parabolic. So we've done that. We've talked about the parabolic nature of a velocity distribution that for laminar flow, where laminar is nice, well-behaved flow, where the flow lines are kind of paralleling one another and not crossing or turning. So here's the x direction Navier-Stokes equation. And we can get rid of some of these terms. That's what we generally do. We start out with the full equation and we try to get rid of terms we don't need. Well, let's go through this. So the first one I've crossed out is because we have steady flow situation. So du dt, the local acceleration, is 0. Let's look at these two terms. The vu is equal to 0 and w is equal to 0. Therefore, these two terms are equal to 0. The last term on the left-hand side has to do with the steady flow assumption. So if it's a steady flow assumption, then some distribution of velocities, we're thinking it's going to be parabolic. I've drawn it poorly there, but parabolic is going to be marching down this tube, and it's going to look the same everywhere. I drew it a little better. So we can just keep going, but it's going to be the same curve everywhere as we march down the line. Therefore, there's really no change of u in the x direction. So it's the gradient here that is 0, making this term 0, even though u is most definitely not 0. Okay, so that gets rid of all the terms on the left side. On the right-hand side, we do have a pressure gradient. After all, how would it flow from left to right here if it wasn't higher pressure on one end and lower pressure on the other? So there is a pressure gradient pushing the fluid through. So we keep this term. We get rid of the gravity term because gravity is going to be in the y direction here only. So gravity is down in the y direction, but it's 0 in the x direction. So that term goes away. Now let's look at the shear terms. So the shear terms, we would have we would have no gradient of x. There's no gradient of x in the x direction. Therefore, this second gradient is 0 too. So this one is equal to 0 in the with respect to the z direction. So coming at us from the z direction, let's think about that for a second. That's coming out of the page. So again, these parabolas will just kind of come out in a curve shape coming out at you, but there'll be no change in the z direction. So the gradient in that direction is also 0. Also 0. Got a box there that keeps highlighting. So these are also 0. And what about this term here in the middle, du dy? So the derivative of the gradient in the y direction, well, this is not equal to 0. It's important to see because you can see this curve, the curves up here have a shape to it. So u does change as you move up and down in the y direction. So you go up and down, u does change. So that term is not equal to 0. So we keep that term. So we end up with these two terms from the x component of the Navier-Stokes equation. Now let's look at the y direction. And if we go through the y direction, we again get rid of this term because of the steady state situation. We have du dv dx, so there's no v velocity, so therefore there's no dv dx, and that one goes to 0. There's no v velocity, so this v term here puts this one to 0. And again, there's no v velocity, so dv dz, that should be a z there. I've drawn it sloppily. So dv dz is also equal to 0. So these terms all go away again on the left-hand side. On the right-hand side, we would have a pressure difference with respect to y because it's deeper on the bottom than on the top. There's more fluid on the height of fluid on the bottom than on the top. So there is a pressure gradient. There is certainly gravity acting in the y direction. But let's talk about shear now. Well, there's no v velocities in this situation. It's all u velocity. So there's none of these shears happening with respect to the y component, to the v component of velocity, or the velocity in the y direction. In this case, we have these two terms. And finally, if we went through this again, and you can try this, but you work your way through it, but the same type of equation would result in only one term, only the pressure term. But actually, yeah, this is kind of a trivial result. It just says that the gradient of pressure in the z direction are coming out of the page. Got the picture up here. So if we come out of it and look at this parabolas coming at us, they would just be the same coming out of the page, and there's actually no pressure gradient in that z direction either. That's why dp dz is equal to 0. So that's kind of a trivial result. So really what we have are some results from the x direction and the y direction that will help us along here. And we really look at, if we look at the equation 1, we can see, or sorry, for equation 2, we can quickly integrate that, separate and integrate these two terms here. So you get dp dy is equal to negative rho g. And we bring over the dy to this side, and you get dp is equal to negative rho g dy. Just simply integrate that, you get a p rho gy and a constant of integration where we let it be a function of x just in case, because if we took the derivative with respect to y, that constant would still go away. Similarly, then, from the first equation from the x direction here, we can bring the dp over, bring the mu over, and we get this 1 over mu dp dx is equal to d squared u dy squared. We integrate it once, and we simply get a y in front of this gradient, this pressure gradient term, because these terms are all constants or a function of x. Therefore, if you integrate with respect to y, you just put a y in front of it, and you get this first constant of integration. We can integrate that one again, and now we get the 1/2 1 over u times dp dx times y squared. So again, just picking up another y, because everything else is either a constant or a function of x. Remember to put a y in front of this constant of integration from the previous problem, and we give it a new constant of integration. Now we have to think about our boundary conditions to figure out what these constants are. And we know that at u equals 0 at the top and the bottom of the plate, in other words, at plus or minus h here, u equals 0. So if we plug that in for plus y equals plus and minus h, you'll find that C1 has to be equal to 0. C2 is equal to 1 over 2 mu times the pressure gradient times h squared. So if we put those back in for the constants, we get this term that's starting to shape up and look like a parabola here. We can write it like this, or we can lump them together this way. And that's our answer. It shows that the velocity distribution inside these two plates, if it's laminar flow conditions, on the basis of the Navier-Stokes equation, should be parabolic.